Aloha! Welcome to our presentation regarding edge, fog, and cloud computing. Let's start with a question. What happens when intelligence no longer resides solely in distant hyperscale data centers, but instead becomes embedded directly within the physical world? What new possibilities emerge when AI can think, react, and learn on vehicles, robots, medical devices, smart grids, and factory equipment, without relying on the cloud for every decision? These questions underpin a profound shift in how modern computing systems are architected. Edge, fog, and cloud computing, once presented as alternatives, now form a unified continuum that distributes computational tasks based on latency sensitivity, contextual relevance, and the scale of data processing required. Rather than competing with the cloud, edge and fog computing extend its capabilities outward, enabling intelligent systems that are not only powerful but also immediate, context-aware, and resilient. Cloud computing anchors the upper layer of this continuum, offering massive storage, global coordination, and the computational power necessary for training increasingly large AI models. Fog computing occupies an intermediate position, pulling selected cloud capabilities closer to the physical environment through regional micro-data centers, smart gateways, 5G base stations, and localized intelligence hubs. Edge computing sits closest to the source of data generation, performing ultra-low latency processing directly on devices such as autonomous vehicles, robots, sensors, and industrial machines. Together, these layers create an integrated architecture capable of supporting applications that demand both real-time responsiveness and global-scale analytics. Autonomous vehicles illustrate this architecture vividly. A single vehicle equipped with high-resolution cameras, lidar, radar, and inertial sensors generates massive volumes of data every second. Because milliseconds can determine safety outcomes, relying solely on cloud communication would introduce unacceptable latency and open the door to catastrophic delays. Importantly, edge computing continues to function even when connectivity is disrupted. This capability is essential in safety-critical scenarios, such as when an autonomous vehicle enters a tunnel or travels through areas with limited or no network coverage. Edge computing solves this by enabling real-time perception, sensor fusion, path planning, and collision avoidance directly on the vehicle, ensuring that mission-critical tasks remain operational even in tunnels, rural areas, or regions with weak connectivity. Fog computing extends these capabilities by coordinating vehicle-to-vehicle and vehicle-to-infrastructure messages, distributing hazard alerts, and performing regional analytics. Meanwhile, cloud systems manage long-term storage, digital twin simulations, fleet-wide optimization, and large-scale training of AI models based on aggregated driving data. This layered model is essential to achieving reliable autonomy and exemplifies how edge, fog, and cloud layers operate collaboratively rather than independently and certainly not in opposition. Artificial intelligence plays a pivotal and inseparable role across all layers of this continuum. At the edge, AI delivers real-time inference using perception models, driver-occupant monitoring systems, predictive diagnostics, and high-speed decision frameworks. Specialized hardware accelerators allow deep learning models to operate under strict latency, power, and thermal constraints. These AI models enable vehicles, drones, industrial robots, and medical devices to interpret complex sensory environments instantly. Fog-based AI complements this by analyzing aggregated data from multiple edge devices, facilitating regional situational awareness and multi-agent collaboration. Smart city intersections can use fog intelligence to adjust traffic flow dynamically. Industrial fog nodes can coordinate robotic cells across a production floor, and hospital fog networks can synchronize patient monitoring systems across departments. The cloud's AI capabilities complete the cycle by training large-scale models that edge and fog nodes continuously update, refine, and redistribute. This continuous circulation of intelligence, training in the cloud, inference at the edge, coordination in the fog, defines the emerging paradigm of distributed AI systems. Beyond transportation, the integration of AI with edge and fog computing is transforming other mission-critical sectors. In healthcare, edge-based AI analyzes vital signs in real time, detecting arrhythmias, respiratory distress, or sudden abnormalities that require instant medical attention. Fog computing integrates this information across hospital departments, enabling cohesive patient monitoring and rapid intervention. The cloud stores long-term records and trains diagnostic models that help clinicians interpret medical data with greater precision. In manufacturing, edge computing supports predictive maintenance, robotic control, and quality inspection using AI-driven computer vision. Fog networks integrate production line information, optimize energy use, and coordinate workflows across facilities. Cloud platforms manage digital twins of factories, enabling large-scale simulations and long-horizon optimization strategies. Smart energy systems likewise depend on this continuum. Edge-based analytics stabilize microgrids and respond to real-time fluctuations. Fog layers manage district-level balancing, and cloud systems carry out forecasting and macro-level planning to integrate renewable sources effectively. Augmented and virtual reality systems also depend heavily on the interplay between AI at the edge, fog, and cloud layers. Edge devices provide instantaneous motion tracking and environmental mapping. Fog nodes synchronize multi-user experiences and spatial intelligence, and cloud servers maintain global scene models, identity management, and the computational heft required to support large-scale simulation. Education, entertainment, telemedicine, and collaborative design increasingly rely on these capabilities. Across all these domains, AI serves as the unifying force that turns raw data into actionable insight, enabling intelligent operations that would be impossible with conventional centralized systems alone. The decentralization of intelligence, however, introduces new vulnerabilities and engineering complexities. Edge devices are exposed to the physical world and are therefore more susceptible to tampering, environmental stress, and inconsistent connectivity. Many edge-based systems collect sensitive personal or operational data, intensifying concerns around privacy, ethics, and regulatory compliance. Fog networks increase the attack surface further by expanding the number of nodes where data passes through. Ensuring trust in this environment requires implementing zero-trust security architectures, secure hardware modules, encrypted channels, continuous patching, and verifiable execution environments. Even beyond security, coordination across heterogeneous hardware remains a core challenge. Edge devices differ widely in capability, operating conditions, and mobility, making uniform deployment, model synchronization, and performance monitoring especially difficult. These challenges highlight the need for intelligent orchestration frameworks, lightweight virtualization, and robust distributed learning techniques. As distributed systems evolve, AI's role within the edge-fog cloud continuum is only becoming more central. Federated learning allows devices to collaborate on model training without sharing raw data, enhancing privacy while reducing communication overhead. TinyML pushes AI capability directly into microcontrollers, enabling intelligence on sensors themselves. Cloud-scale models provide broad contextual intelligence that edge and fog nodes adapt locally. Digital twin ecosystems synchronize real-world environments with simulations, benefiting from continuous data streams originating from edge and fog nodes. The growing deployment of 5G and the emergence of 6G will significantly reduce communication delays, enabling new tactile applications such as remote surgery, collaborative drone swarms, and industrial teleoperation with near-instantaneous feedback. All of these developments prompt us to reflect on larger societal and philosophical questions. What will it mean when intelligence becomes ubiquitous, embedded in nearly every device, every system, and every physical environment we interact with? How should we design ethical frameworks that guide AI-driven decision-making at the edge, particularly when those decisions involve safety, privacy, or human well-being? And as we push computation outward into this fast-paced world, how can we balance innovation with responsibility, ensuring that distributed intelligence enhances rather than undermines trust, transparency, and social good? If these questions resonate with you, I invite you to share your thoughts and join the conversation. Your insights matter. Please add your comments, like the post if you find it meaningful, and subscribe to continue exploring the future of intelligent, distributed systems. Thank you for watching. Mahalo.